Acceleration, in physics, is the rate at which the velocity of an object changes over time. An object's acceleration is the net result of any and all forces acting on the object, as described by Newton's second law. The SI unit for acceleration is the metre per second squared. Accelerations are vector quantities and add according to the parallelogram law. As a vector, the calculated net force is equal to the product of the object's mass and the acceleration. For example, when a car starts from a standstill and travels in a straight line at increasing speeds, it is accelerating in the direction of travel. If the car turns, there is an acceleration toward the new direction. For this example, we can call the accelerating of the car forward a linear acceleration, which passengers in the car might experience as force pushing them back into their seats. When changing directions, we might call this nonlinear acceleration, which passengers might experience as a sideways force. If the speed of the car decreases, this is an acceleration in the opposite direction, sometimes called deceleration. Passengers may experience deceleration as a force lifting them away from their seats. Mathematically, there is no separate formula for deceleration, as both are changes in velocity. Each of these accelerations might be felt by passengers until their velocity and direction match that of the car. Definition and properties. Mathematically, instantaneous acceleration acceleration over an infinitesimal interval of time is the rate of change of velocity over time, that is, the derivative of the velocity vector as a function of time. Here and elsewhere, if motion is in a straight line, vector quantities can be substituted by scalars in the equations. Average acceleration over a period of time is the change in velocity divided by the duration of the period. Acceleration has the dimensions of velocity divided by time, that is, lt2. The SI unit of acceleration is the metre per second squared. This can be called more meaningfully metre per second, as the velocity in meters per second changes by the acceleration value, every second. An object moving in a circular motion such as a satellite orbiting the Earth is accelerating due to the change of direction of motion, although the magnitude may be constant. When an object is executing such a motion where it changes direction, but not speed, it is said to be undergoing centripetal acceleration. Oppositely, a change in the speed of an object, but not its direction of motion, is a tangential acceleration. Proper acceleration, the acceleration of a body relative to a free fall condition, is measured by an instrument called an accelerometer. In classical mechanics, for a body with constant mass, the acceleration of the body's center of mass is proportional to the net force vector acting on it. Where F is the net force acting on the body, m is the mass of the body, and a is the center of mass acceleration. As speeds approach the speed of light, relativistic effects become increasingly large and acceleration becomes less. Tangential and centripetal acceleration. The velocity of a particle moving on a curved path as a function of time can be written as with v, t, equal to the speed of travel along the path, and a unit vector tangent to the path pointing in the direction of motion at the chosen moment in time. Taking into account both the changing speed v, t, and the changing direction of ut, the acceleration of a particle moving on a curved path can be written using the chain rule of differentiation for the product of two functions of time as where on is the unit normal vector to the particle's trajectory, and r is its instantaneous radius of curvature based upon the osculating circle at time t. These components are called the tangential acceleration and the normal or radial acceleration. Geometrical analysis of three-dimensional space curves, which explains tangent, normal and binormal, is described by the Frenetter-Serret formulas. Special cases, uniform acceleration. Uniform or constant acceleration is a type of motion in which the velocity of an object changes by an equal amount in every equal time period. A frequently cited example of uniform acceleration is that of an object in free fall in a uniform gravitational field. The acceleration of a falling body in the absence of resistances to motion is dependent only on the gravitational field strength g. By Newton's second law, the force, F, acting on a body is given by due to the simple algebraic properties of constant acceleration in the one-dimensional case, there are simple formulas relating the quantities displacement s, initial velocity v0, final velocity v, acceleration a, and time t. Where equals displacement, equals initial velocity, equals final velocity, equals uniform acceleration, equals time. In the case of uniform acceleration of an object that is initially moving in a direction not aligned with the acceleration, the motion can be resolved into two orthogonal parts, one of constant velocity and the other according to the above equations. As Galileo showed, the net result is parabolic motion, as in the trajectory of a cannonball, neglecting air resistance. Circular motion, uniform circular motion, that is constant speed along a circular path, is an example of a body experiencing acceleration resulting in velocity of a constant magnitude but change of direction. In this case, because the direction of the object's motion is constantly changing, being tangential to the circle, the object's linear velocity vector also changes, but its speed does not. This acceleration is a radial acceleration since it is always directed towards the center of the circle and takes the magnitude. Where is the object's linear speed along the circular path? Equivalently, the radial acceleration vector may be calculated from the object's angular velocity. Where is a vector directed from the center of the circle and equal in magnitude to the radius? The negative shows that the acceleration vector is directed towards the center of the circle. The acceleration and the net force acting on a body in uniform circular motion are directed towards the center of the circle. That is, it is centripetal. Whereas the so-called centrifugal force appearing to act outward on the body is really a pseudo-force experienced in the frame of reference of the body in circular motion, due to the body's linear momentum at a tangent to the circle. With non-uniform circular motion, that is, the speed along the curved path changes, a transverse acceleration is produced equal to the rate of change of the angular speed around the circle times the radius of the circle. That is, the transverse acceleration is directed at right angles to the radius vector and takes the sign of the angular acceleration. Relation to relativity, special relativity. The special theory of relativity describes the behavior of objects traveling relative to other objects at speeds approaching that of light in a vacuum. Newtonian mechanics is exactly revealed to be an approximation to reality, valid to great accuracy at lower speeds. As the relevant speeds increase toward the speed of light, acceleration no longer follows classical equations. As speeds approach that of light, the acceleration produced by a given force decreases, becoming infinitesimally small as light speed is approached. An object with mass can approach this speed asymptotically, but never reach it. General relativity. Unless the state of motion of an object is known, it is totally impossible to distinguish whether an observed force is due to gravity or to acceleration. Gravity and inertial acceleration have identical effects. Albert Einstein called this the principle of equivalence, and said that only observers who feel no force at all including the force of gravity are justified in concluding that they are not accelerating. Conversions, see also. References. External links. Acceleration calculator, simple acceleration unit converter, measurespeed.com, acceleration calculator based on starting and ending speed and time elapsed.